Hello everyone, and welcome to today's chem lesson. Today, we are going to talk about the last kind of bonding. We are going to talk about metallic bonding, and how that is different from ionic bonding or covalent bonding. Now, if we remember our talks of ionic bonding occurs when there is a metal and a nonmetal. And covalent bonding occurs when there is a nonmetal and another nonmetal. The last combination of elements is a metal and a metal, and that's where metallic bonding occurs. When two metals bond, they have a special kind of bond, a sharing but not quite kind of bond, where the nuclei of the atoms are repelling each other, right, held in place by their repelling forces, which we're going to draw out in a minute. And the electrons, instead of being shared directly between two nuclei, are actually pooled together and can move freely around the nuclei, which creates something that we call the sea of electrons. Now, this combination of phenomenon here, right, the nuclei held in place by their repelling forces, and the electrons moving wherever they want or wherever they are needed, is what allows metals to be metals. What allows them to be a good conductor. It's what allows them to able to be hammered into different shapes and bent around and turned into wires and made into everything that they are used for. Let's take a look at what this actually looks like. In a metallic bond, you end up with a bunch of positive nuclei arranged in nice, even rows and patterns, and I'll show you in a minute why they stay this way. Right, this happens this way, this way, this way, this way, out of the page towards us, and behind the page. Right, this happens in all dimensions. So there's something directly in front of this one and directly behind this one. Now that is going to force this nucleus to stay exactly where it is. If this nucleus moves this way, it gets repelled by the other positive nucleus. This way, repelled by the other positive nucleus. This way, repelled by the other positive nucleus. If it comes out of the page or behind the page, right, no matter which direction it goes in, there are positive nuclei to repel it and keep it in place. Remember, since this kind of goes to infinity in every direction, it happens to every nucleus. They are locked in place because they can't move without being repelled back to where they came. Now, the electrons themselves, they get pooled together. Right? Metals have small numbers of valence electrons. They're not going to be able to share in a way that makes everybody happy. They're not going to be able to transfer in a way that makes everybody happy. And so they pool together their electrons, and that allows the electrons to move wherever they are needed, wherever they want to move, wherever they are pulled to. And these electrons kind of move around within this framework of positive nuclei, constantly moving. And also helping to hold these nuclei in place, because the nuclei are attracted to the electrons. Now, what does this do for us? Right? Why is this important? Why does this allow metals to be hammered into different shapes? Right, let's think about that. Here comes a hammer. If I take a hammer and I hit this nucleus, and we're going to erase our electrons because I have no choice. If I hit this nucleus with enough force, it's going to move down. If I put enough force into it, it's actually going to shift the other nuclei down, right? It will be repelled. There's been some pushback because there's positive nuclei. But if I push this down with enough force, it's going to move all these nuclei out of the way. Because it's not held together by a bond that can just break. It's not held together by an attraction that can just be broken. If you hammer something covalent, it will break. If you hammer something ionic, it will break. If you hammer something metallic, it will shift. It will move and accommodate that force because it has the built-in capability to do so. And then when we get our electrons back, they're going to accommodate that as well. Right? When we redraw these electrons in, they're going to move around, right? They're not going to stop the hammer from hitting. They're not going to stop anything from happening. But when these electrons come back in, they do the same thing they did before. Why does this phenomenon make metals good conductors of electricity? Well, for that to be defined, we need to talk about what electricity is. Electricity is moving electrons. Electrons going from point A to point B. Since there's no defined path for the electrons here, I can have the electrons take this path through the metal. Starting at point A, ending at point B. Starting on the left, ending on the right. And there's infinite paths. Because the electrons can go wherever they want, there's infinite paths for these electrons to take. Moving throughout the metal as they so choose, as they are pulled, as they are pushed by whatever forces there are. And so this sea of electrons phenomenon is what allows metals to behave the way that they do, the way you're used to seeing them behave. Why you can bend a piece of metal and it won't break immediately. Why metals are great conductors of electricity, and also why covalent and ionic things are poor conductors of electricity. Right? We're moving charge for electricity. We're moving electrons for electricity. And the only type of bonding that really allows those electrons to move where they want is metallic bonding. And with that, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.